Thank you, and thank you very much for the invitation to come and speak with you today. The title of this presentation is AI and Climate, and I'm going to run through some examples of how we think using data science and AI can actually help us address some of the major challenges associated with climate change, environmental change, and also to allow us to develop adaptation and mitigation strategies. My name is Professor Gavin Shaddick. I'm from Cardiff University. Before I joined Cardiff last year, I was a fellow at the Alan Turing Institute for 5 years, the UK's National Data Science and AI Institute. So, brief outline of my presentation. I'll go through some background to AI and environmental challenges. I'll then run through some examples from work we've done both at Cardiff and at the Turing. And then I'm going to introduce a risk framework known as hazards, exposures, and vulnerability as a way of thinking about how we might use AI to bring data together from different spheres to come up with solutions. And then finally, I'll end with some conclusions. So I think we're all aware that the interaction between ourselves and the environment is absolutely crucial that we get it right. It affects everything, all aspects of society, our health, wealth, safety, future development. And as we've got AI tools now developing to a very sophisticated level, and an explosion in the amount of data that's available, whether that be from the internet, whether it be from remote sensing satellites, from monitors, also from personal devices, we have an exceptional opportunity to transform our understanding of the complex interactions between ourselves, the climate, the environment, natural ecosystems, human, social, and economic systems. So if we can unlock the full power of that data that is now available, we'll have wide-reaching impact across all sorts of areas. Different sectors, both those directly related to the environment, such as agriculture, fisheries, water, waste, but also things like transport, infrastructure, health, energy systems. So everything really interacts with our environment. And as the climate is changing, as in certain parts of the globe, temperatures are increasing, how do we make sure that we can become resilient to those changes and actually make sure that we can thrive? There are, of course, challenges. There's lots of data out there, with data from satellites, monitors, and lots of other sources, but that data is often out of date. So how do we make decision making if we've got out of date data? Or there might be a lot of data in certain areas of the world, but there might be regions where there's very little data. So how can we use AI to fill in those gaps in data? Often the data is available on large aggregated areas such as country level, and we really want to know what's happening in our cities or in our neighborhoods. So how do we take data that's available at a country level, or maybe from a satellite looking at large areas, and actually integrate that with local data to get local insights? And if we think about the Sustainable Development Goals, there are 17 Sustainable Development Goals, and behind those are indicators. So there are metrics which are measured to see if we are making progress. The problem is the United Nations Environmental Programme suggests that out of this 93 environmental related SDGs, there isn't enough data to track or monitor for nearly over two-thirds of them. So that means across many parts of the world, we can't actually understand whether things are getting better or worse. And if we don't understand the situation, how can we possibly understand how we're going to solve the problems? So the good news is there is a lot more data that's available. So there's a rapid increase in the number of variety of data sources related to the environment. That comes from remote sensing satellites, Earth observation, from monitors, from personal devices, also from large numerical mathematical models. If we think about climate models, they are hugely complex physical models, mathematical models, full of partial differential equations. They run on very large computers, and they can predict the changes in the climate over the next 50 years. The problem is they are available on large grid cells. So if we look at the example on the right-hand side, some of the outputs of climate projection models might be on a 50-kilometer by 50-kilometer grid cell. But what about if we want to know the effect of increasing temperatures, for example, in our neighborhood? How do we go from a large-scale piece of data down to something very local? Also, these are very different sources of data. If I have an Apple Watch, other watches are available, that's recording information, that is a very different source of data than from something from an air pollution monitor next to a road, or a pixel image from a satellite. So we need to understand the different biases in those data, why those biases might change over time, they might change over space. We also know that most data sources come with some form of uncertainty. So if I have a well-calibrated scientific monitor, that's going to be a lot more accurate than if I have a very cheap sensor that I'm putting on my lapel. So we need to understand those different biases, we need to understand those different uncertainties, and as we put data together from different sources to come up with new data products, to answer questions, to gain insights, we need to understand the data journey. Where has that data been? What has someone done to it? What processing might they have done, which means that it might not be quite what we think it is. So increasingly, we're going to have to understand the data generation mechanism, and we're going to have to understand which data sources we really trust and which ones we might want to calibrate or compare with other data sources before using them. So climate, environmental change is inherently a global challenge. It affects the entire world, but what we want is regional and local solutions. So the sheer volume of data out there means that we have to use AI. We're going to have to augment human intelligence. There is no one in this room, I don't believe, certainly not me, could take in all the data based on the environment, come up with an idea, and then come up with a solution. And gone are the days that we could just download all the data to our own laptops. We're going to have to think about using AI, all facets of AI, multidisciplinary. We need to care about data quality, data accuracy, how we combine data, what questions are we answering, what questions should we be answering, and then think about how we embed that into decision-making processes, and actually embedding that into things that will make climate change less of a threat. So I'll now go through some examples. These are from the organisations at the bottom: Cardiff, University of Exeter, the UK Met Office, Turing Institute, the UK Clean Air Programme, and CSIRO in Australia. Before I go through those examples, I thought it might be useful to look at the UK government's AI strategy. My favourite page is page 45, which is on AI and net zero. And you can see some of the examples that are listed in that document about how AI and machine learning might be able to help us to our journey to net zero. But one key fact that is written in that document is, though AI applications are being well integrated into many sectors, commerce, energy systems, and some operations, in climate and net zero, they're relatively underdeveloped. And there's an awful lot of potential, and certainly from taking advances in technology from other sources and actually using them to help us address the problems of climate change. So some examples. I've talked about SDG indicators very briefly. On the left-hand side, you'll see a map of the world, and that is shows the locations of air quality monitors in the WHO, World Health Organization's database. Now, what do you see? You see a lot of information in North America, Western Europe, increasingly India and China, but there are large parts of the world where there aren't any routine monitoring, high-quality air pollution monitors. The problem is, one of the SDG indicators, 11.6.2, means that we have to be able to understand air pollution in every city and every country in the world. So the question is, how do we go from that map that has a lot of grey to that map which is fully coloured in? Now the answer is something called the Data Integration Model for Air Quality, DMAC, which was developed by myself with the World Health Organization. It takes satellite information, numerical models, chemical transport models, land use, road networks. It integrates that in an AI model. For those who are interested, it's a Bayesian hierarchical model with dependencies over space and time. And it allows us to predict air pollution on a very high resolution grid all over the world. So now for the first time we can actually calculate that SDG indicator because we have information on the concentrations of air pollution absolutely everywhere. And there really is no limit to the resolution. We could do higher and higher resolution maps. The only thing stopping us really is computing power. On the right-hand side is an example of where we worked with an electricity distribution company, Western Power Distribution, in the UK to monitor and predict electricity demand. So in order to monitor electricity demand, WPD, Western Power Distribution, wanted to put monitoring devices in every primary substation, so in every electricity substation, but that's very expensive and there are lots and lots of substations across the UK. So what we did was we put some monitors in a small selection of substations in South Wales, and then we augmented that with other data that was routinely available and built a predictive model. And that allowed us to predict electricity demand even when there was no monitoring, which was a far cheaper and much quicker way than installing monitors. So some more examples. One on the left-hand side is the CLIMA model, Climate Impacts Adaptation Resilience, where we integrate data on hazards, exposures, and vulnerabilities, different data sources, in order to come up with ideas for climate solutions. And the other is looking at climate change and integrating that with agricultural models to see where there might be changes in conditions that would lead to us needing to think about growing different crops and thinking about different diseases that might be prevalent in the future. So hazards, exposures, and vulnerabilities. What we're really doing here is to think about climate hazards. Let's think about increased temperatures or increased rainfall. There will be areas where there'll be an increased temperature. Then we need to think, what is exposed to that temperature? If it's a human being, if they're exposed, there's a higher temperature, are they vulnerable? Older people with pre-existing health conditions might be more vulnerable than those who are healthy and younger. So we need to be able to integrate different types of data from different sources and bring them together. So we bring together hazard data, that might be climate projections. We bring together exposure data, that might be the locations of settlements. It might be the locations of electricity power plants. And we bring together vulnerability data. That might be, if a power plant is flooded, does it have good flood protection? If a human being is exposed to high temperatures, do they have a pre-existing condition? And a few examples of this, we developed a tool for Bristol City Council in the UK. We overlaid climate projections and what might happen to the temperatures with building characteristics and looked at the effect of what retrofitting to buildings might be able to do. Could we put double glazing in? Could we put white or green roofs to try to cool the temperatures in buildings? We overlaid that with hazard information, that was temperatures going forward 40 years, and then we overlaid that with vulnerability information, and that was health-related data and demographics, so how many old people lived in certain areas. And as you can see, we built an AI tool to combine these information and actually to predict for Bristol City Council how many extra hospitalisation cases there might be each summer. And we brought that together in a front end which allowed the council policymakers to try different scenarios, to try different retrofitting, to look at different areas and think about how they might invest now to reduce the problems of climate change. Another example was Credo, which was a climate resilience demonstrator for the COP26 conference in Glasgow a few years ago. This was a digital twin where we integrated climate projections and future potential flooding with hydrological models, and we had an AI emulator to make the speed of the running models much quicker. We then integrated that with information on the infrastructure. road networks, transportation networks, electricity networks, and then we had information on how vulnerable they might be. And what we wanted to know in the digital twin was to use that to see whether there might be any cascading hazards. So if there was flooding of electricity power station and the telecoms network, the power station would not be able to contact the power distribution company to go and fix the problem. And if the road network was flooded, then people might be without electricity for a long time. Also, we overlaid the resilience of the electricity network to think, well, if one power station goes out, it might not be a problem. But if two consecutive ones goes out, you could have large areas that were without power for a long time. And the digital twin allowed people to actually run scenarios, different flooding scenarios, put in different resilience scenarios, and work out what the best investment resources was. I'm running out of time, so I'll run very quickly through this last example. We used agent-based modeling, which is where we have virtual individuals. We might have a virtual school child who goes to school, and we developed this as part of the response to COVID-19 in the United Kingdom, a project led by the Royal Society. Those virtual individuals then go to school, they go to the supermarket. If they bump into a virtual individual in the supermarket who has COVID, there's a chance that they will pass COVID on. Then the person who's just caught COVID goes around their virtual life, a bit like SimCity. And so we can model the spread and the reduction in the pandemic. It also enables us to put in lockdowns. And we were able to use this to predict the effects of different lockdowns, whether lockdowns started earlier or later, and depending on their length. We then adapted this after COVID to looking at exposures of individual people in populations to things like heat with climate change and air pollution. And you can see on the right-hand side, this isn't a video, it should be, that actually the model runs and you can see the spread of COVID disease and the reduction. You can tweak, you can put in lockdowns, you can shut down supermarkets, you can shut down schools, and you can really run through and see the effect of those different decisions. So, in conclusion, there is a huge potential for data science and artificial intelligence to play a crucial role in addressing the challenges associated with environment change. If we think about climate change over the next 30, 40 years, in most countries, there'll be increased heat, there'll be increased periods of intense rainfall. In some countries, it will get much colder. How do we make sure that our infrastructure, how do we make sure that our hospitals, how do we make sure that we as human beings are ready for those changes? What can we do to adapt to climate change and make those adaptation strategies now based on the very best information? And so AI is going to help us bring together all this new data, plus what we understand at the moment, to bring new insights and new information. In order to do this, we do need to collaborate. AI scientists need to collaborate with end users, the public, stakeholders, whether that be businesses, governments, and industry, to make sure that we really understand the problems that need to be solved. If we think about the power distribution network, we need to understand how that works when it's in crisis so that we can model it using AI.